Hello, I'm back to do the second type of electron configuration, which is a variation of a ground state electron configuration called a condensed electron configuration. And what the condensed electron configuration really helps with is identifying the valence electrons, really visually apparent in a condensed electron configuration versus what we call the core electrons, which are on the inside. Okay, so we're going to start with a regular ground state electron configuration for the element gallium, and then I'll show you how you would use that electron configuration to write a condensed electron configuration. Okay, and you guys should just know that I always have my periodic table handy with me when I'm doing these. I don't remember, where these guys are at on the periodic table. And I've done so many of these that now I don't even like think about the filling chart per se, but I kind of look at the periodic table and use the filling order that I know from the periodic table. So once you get some practice, you guys, I think will start to feel more comfortable with this. Okay, I'm going to put at the bottom here, again, these max counts of electrons that can go in these orbitals. I'm going to put this one on here, but remember, we're never going to, you guys won't be writing electron configurations where elements have electrons in f orbitals, but we'll put it down there just in case. All right, so remember I'm placing 31 electrons, and I'm going to start with this guy right there, 1s, and it's going to have 2. And then I'm going to go to the 2s, so down, kind of, and down to the 2s, and I'm going to put 2 in there. And then the next one down and back up is the 2p, and that's going to be 6, and then 3s, 2. Well, let's see where we're at in terms of our count. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12. So I need to keep going. All right, so after the 3s, I'm going to go to the 3p, and that one's going to have 6 again. And then I'm going to go to the 4s. Put 2 in there. So now I'm like 2 plus 2 is 4, 10, 12, 18, 20. So I need 11 more. All right, so then I'm going to go to the 3D, and remember those D's can have 10. 3D, 10. And now I have 10, 12, 18, 20, 30, and I only need one more. So now after the 3D comes this 4P. So look at this like weird thing right there. It goes a little bit out of order. And that's the thing with those transition metals. So I'm going to have this 4p. And remember, I can put 6 in there, but for gallium only has 1 in that orbital, right? It only has 31. So it can hold 6, but there's only 1 in there. And that is the ground state electron configuration for gallium. Now, how do I use this to write the condensed electron configuration? Okay, so I know that I have the element gallium. Now, what I do when I write the condensed electron configuration is I'm going to represent what we call the core electrons, the innermost electrons, by writing the symbol of the noble gas that has fewer electrons than gallium, that's the closest to gallium. And the way that I can see that is by sort of looking at my periodic table here, and I'm going to look at gallium in row 4. I'm going to go up a row, right above it is aluminum, and go all the way to the right, and that is argon. And argon has 18 electrons. Now you can see that the one krypton is actually closer, but has more electrons than gallium. So you want to choose the one that has fewer electrons. So up a row and all the way over to the noble gas on the right. So this condensed electron configuration sometimes is actually called the noble gas electron configuration because you're going to write the noble gas symbol for that in brackets. So gallium, that's what we're doing here. So I'm going to write a little square brackets, and I'm going to put the noble gas again that we chose, which was argon. I'm going to just write the symbol for argon. Now, the electron configuration of argon is 1s2, 2s2, 2p6, 3s2, 3p6 for this whole part right here. And so basically me writing this right here is the same as writing this. And so now I'm going to write everything else that comes after that. And those are what we would call the sort of outer shell electrons. So then I just keep going. Okay. Now, these are called core electrons, and these are outer shell. Here's the trick though, and especially for something like gallium, it's really important that has d electrons and d orbitals. Not all of these are valence electrons. So it's really important for us to note that the valence electrons are only going to be the highest number s and p electrons. So I'm going to reorder this, and this is what you guys are going to do. So then I'm going to put this 3D before this. All right, so I'm going to rewrite this, and this will be your final answer. I'm going to put that 3D first because those electrons, even though they have a little bit more energy than these 4s ones, and we know that because it fills afterwards, they're actually closer to the nucleus. So they're moving a little bit faster, but they're actually closer to the nucleus. And so when we do chemistry on atoms of gallium, the ones that are actually going to leave are this 4s1 and this 4p1, or sorry, 4s2, these 2 electrons here, and the 1 electron there. So gallium is a metal that would form a charge of +3. All right, so then I'm going to write 4s2, 4p1. Now these are my valence electrons, right? And there are 3 total. Okay, so that is the condensed electron configuration. So the trick here is when you write the electron configuration, you're going to find your element on the periodic table. You're going to go up a row and all the way to the right to the noble gas that has fewer electrons than your element you're trying to determine. You're going to put that symbol in brackets, and then everything else that comes after that, you're going to write out longhand. Then you're going to reorder it if you need to put anything that has a lower value of n in front right after the brackets, and then reorder so that the same number values of n are together with the s coming before the p. All right.